When last we spoke, I was talking about physics as a description of the universe, and I'm going to describe my universe by making measurements using a device like this ruler here, meter stick. This meter stick has precision in that it has a number of tick marks on it. This meter stick is actually special, a nice educational meter stick. It has exactly what you want in a meter stick on this one side here. It's got millimeter tick marks from one end to the other, making it possible for me to measure things from 0 to 1 meter long down to a precision of 1,000th of a meter. And precision is good because the more precise a number is, the more opportunity there is for significance in the figures, the more information I get. But if I take this meter stick and I turn it, I find it has a side that quite strangely has ½ centimeter tick marks on it. It has fewer tick marks. Well, Shadli, isn't that less useful? Yeah, it's less useful. It's education. It gets even worse if I turn it again and I realize that it has decimeter tick marks on it. Tick marks every 1/10 of a centimeter. It's getting worse. And this is actually, it's almost like a joke. It's got a side that technically has 1 tick mark. Meter, right? Isn't that bad? Sure. How big is Friel's head? It's a meter. Precision in measurement. The reason why it matters is that every measuring instrument that I can possibly use to measure my universe has a certain limit to its precision, which means every single measurement that I make is uncertainty in measurement is the issue of the day. Uncertainty in measurement. Now, yesterday we talked about sig figs, and that may have been a boring discussion, simply identifying the number of significant figures in a measurement. Today, I'm going to talk about the uncertainty in the measurement. And you may think, why? It's just a thing I'm going to do. How does it matter? Well, I'm going to show you how it matters in a really, really powerful way that's going to demonstrate to you, I hope, the value of understanding how uncertainty affects our measurements, because our measurements help us define, describe, and understand our reality. I'm going to ask you to do something extraordinarily simple. And I'm going to give you a simple instruction, and when I do, you're probably going to want me to give you some details. After I say ready, set, go, you're probably going to think, well, no, hang on a second, wait, I have a question. I'm not going to answer any of your questions. I'm simply going to tell you what I want you to do, and I want you to do it. And we'll see how it works out. You have one of these meter sticks with you at your table. What I would like you to do is to use the meter stick to measure the length and the width of the table. When you have the length and the width, use the length and the width of the table to calculate the area of the table. It doesn't get any simpler than that, right? We're not splitting the atom here. Calculate for me, to please, the area of the table by first measuring the length and the width. And when you have your area, send one representative from your table up here to the board where we will collect your answers. And we'll see what we get. So please, area of the table, calculate, and report. Go. Small centimeter. 10 tables measured, 10 measurement. While all this was going on, a few observations. As soon as you get into measuring the tabletop, some questions start to happen. First of all, when you investigate closely, the table has a bevel on it, doesn't it? So did Shadli mean the outside of the bevel or the inside of the bevel? Because the answer is going to be different depending on which one you choose. Also, you take your meter stick, and your meter stick's not long enough to measure the length of the table. So how do you do that? What's the correct procedure? Maybe there isn't a correct procedure, the best procedure. Lots of putting the finger down, moving along, doing things like that. Do they affect the outcome of the measurement? Absolutely. So what I measure and how I measure it matters. It matters a great deal. Turns out it doesn't matter to this particular exercise and the reason why we're doing it, but let me take a moment. I asked you to measure the length and the width of the table. I did it very simply. And I said that I wouldn't answer any questions. And the reason why is that there are immediate questions. Not only are there questions about the bevel, but believe it or not, dig this. The length and the width of the table have a problem of definition. What does it actually mean, the length of the table? We say, well, here's one end of the table, here's the other end of the table, and the distance between them is the length. Yeah, but when you measure that, the measurement is uncertain. Well, yeah, sure. Shadli, you just gave us this crappy ruler. Perhaps if we measured it in a more sophisticated way, we'd get a more precise measurement. Well, yeah, you would. You're right. But that measurement would still be uncertain. You still wouldn't know. You said, no, you don't understand. We're going to make it really fancy. We're going to get laser beams and stuff. We're going to get real legit scientists in here. We're going to do it up in the best way known to human science. Yeah, but it's still uncertain. See, but it's worse than, because you know that material substances like the tabletop are composed of atoms and molecules, and that those atoms and molecules are vibrating with an average internal kinetic energy that we call temperature. So through those vibrations, the table's getting longer and shorter constantly. Sure, on a molecular level. So lots of folks who aren't interested in sciencey things might say, well, it doesn't matter. But ultimately, does the table have a... No. The length of the table is abstract. And in our human measurement, we treat it as absolute. So when I ask you to measure the length of the table, that's a strange thing. And yes, we also have to train you to use the measuring instrument properly so that no mistakes are made in the measurement. You have to be careful how you do things. You can't be sloppy. If you're sloppy, you make mistakes. And that's happened a lot historically in science. Sloppy execution of an experiment results in mistakes that can sort of mess things up for a long period of time. But let's assume all of that's done properly. You've all measured the table, and you all got an area, and you all wrote it up on the board. And the suspense is killing me. Which one's right? Which one's the right answer? Because I see a lot of different answers. Now let's look at them all here. I got 10 different answers to look at. Any of them the same? Did we get a situation? Right here, I got 9,333 and 9,333. Check this out. They're not the same, are they? Because this is square millimeters and this is square centimeters, right? And that's the thing that happened. And that's part of the observation that I make while I was watching you do it. I've got a stunning bit of news, really important. We do not live in a scientific age. No, hang on a second, Charlie. I got an iPhone. It's amazing. I can call anywhere. It's a global positioning and whatnot. I can get movie tickets. Look at that. Woo, yeah, okay. I can FaceTime with my friends and communicate over long distances. Pretty soon people are going to be buying tickets to go into space as tourists. We're going to be on a mission to Mars. Of course we live in a scientific age. No, we live in a technological age. We live in a technological age. And what I'm describing here is that we do not live in an age where we think scientifically about things. This is sort of an important issue for me right now. It's a thing that I've been thinking about, and it's not a finished thought. But I've been wondering what are the characteristics of our current age, our society that we live in, that are not scientific at all? They're characteristics of our age. There's a couple that I've come up with. One of them is populism, believing in the idea that most people believe in. So if I had a couple of answers and in a previous block, I had 3 or 4 answers that were the same. Surely if people measure the table and they all get the same answer, that must be the right answer. The most common answer, the right answer. That is not scientific thinking, that is populism. Another thing is confirmation bias. That is, I'm looking for confirmation of the thing that I already believe. That is not scientific to think that way, to behave that way. But when someone comes up to the board and writes a 9, you're back there, you did yours, you're like, oh, I don't know. But as soon as you see the 9, you go, good, I got a 9. No, good. But then there's a 3 and mine is a 2, but then someone else writes a 2, so you got a 9 and a 2 and everything's great. That's not scientific thinking. That's unscientific. There are a couple of special things that happened with this one. This rarely happened. 9,300. Do you know why that happened? You did this. Why did you? You had a bunch of other numbers there. They were perfectly nice. Why didn't you give us those numbers? Why are you cheating us? I didn't ask him to, but he thought about the significant figure. And I bet some of you, when you saw that number go up, thought, oh, significant figures. Oh, he burned all of us, being super smarty with the science, only reporting the number to 2 significant figures. Well done, well done. And everybody goes, oh, the jig is up. And he may even believe, oh, I got Shadley. Shadley thought I wasn't going to. So, that answer is a very sciencey answer. Not as sciencey as this answer. Not only were the significant figures changed here, wrongly, by the way. How many significant figures does this have? 3. In scientific notation, all digits are significant. So this has 3, so nice try. If it had 2, it'd be even more sciencey because it's written in scientific notation. Must be science. Come back to my question. And I think which one of these is right? None of them. They are all wrong. You're like, nah, Shadley, I used to write numbers significant figures. Well, if that were the only issue, then that would be great. So well done. All of these are wrong. Part of the reason for that is that we don't live in a scientific age. Measurements, which are our observation of the universe, which is how we understand everything in all of measurements are inherently uncertain. And it's impossible to draw a conclusion from measurement without appreciating the uncertainty in the measurement. Now, Here's what should have happened. If we had all in this room made the measurement scientifically and reported it scientifically, everyone would have written the same answer from the top to the bottom. Don't think, oh, mine's right, it's just that everybody else, no. They're still wrong. They're all wrong. Everyone would have written the same thing. So here's the wonderful thing that's going to happen. I can't believe that you're as bad as you seem, so I'm going to train you how to make measurements and calculations scientifically. A little bit of training, I'm going to train you up, and then we're going to come back and do this activity again, a couple of days. And when we do, you're all going to get the same answer. Well, what good does that do? We're not going to make any money off it. But along the way you perceive your universe will change. As a matter of fact, it's going to change a little bit today. So some careful thinking and a little bit of a warning. What I'm about to do is demonstrate skills that I'm going to expect you to have. So if you're getting a little drowsy, shake it off, because here comes the actual physics of this, and you're going to be expected to do it. So here we go. Here I am back with my 2x4 that I'm measuring the width of. And I'm using a centimeter ruler that has millimeter tick marks on it. And I want to make this measurement in a scientific way. Well, the first thing I'm going to do is make sure that I use it properly. So here it is, holding it up against this edge of the 2x4. You say, wait a second, so the edge of the 2x4 is a little round, and maybe the 2x4 changes depending on where you are in the length and the difference of things and whatnot. Yeah, all of that matters. But some of that is beyond my control, right? I use the instrument to my best capacity to do the best I can. I don't do it, I go, oh, I don't know, it's like that. No, I do it carefully, right? Carefully made measurement. And when I do, 1, 2, 3, 4, 5, 6, 7, 8, it doesn't make it to 9. So I guarantee you 100% without hesitation, that board is 8 centimeters wide, plus or minus. I've got more. So I count out 1, 2, 3, 4, 5, 6, 7, 8 tick marks. There it is, right there. And it's a bad situation up here because I got pixels from the projector I'm looking at. It's closest, the edge to me seems closest to the 8th millimeter tick mark. So I'm going to report this as 8.8 because it's closest to that tick mark. But there is uncertainty in this measurement as there is uncertainty in every measurement that's made ever anywhere. Uncertainty in the measurement. And how do I deal with it? The ironic thing here is that you know how it's done, but you've just never seen it. You've never been trained, which is really the sad part. And it's all wrapped up in the fact that we do not live in a scientific age. The way that I account for the uncertainty is I write plus or minus 0.1. It's a bit of information that I provide to the consumers of my science, the people who look at it, judge it, and use it for practical purpose. It reports on the quality of the measurement, because some measurements are good and some measurements are bad. Some measurements are easy to make, some measurements are difficult. And unless I report the uncertainty of the measurement, then I am not doing science. You've seen the plus or minus 4, yeah? Yeah? You see it a lot. Read an article in the New York Times about a science issue. There are numbers in, right? How often do you see the number with a plus or minus? How often do you see a number reported along with the uncertainty in the number? The answer is almost never, which makes you wonder. If a number can be presented to you without its associated uncertainty, how easy to lie to you? Pretty easy. For example, imagine I measure the 2x4. I use, you know what I need? I need a 2x4. Which I just happen to have, a 2x4 for discipline. Let's imagine that you've never seen a 2x4 before. You ask the question, how wide is a 2x4? Shidley, I say, well, I don't know, but I'll measure it and I'll tell you. You say, well, thank you, Shidley, I appreciate that. No problem. Get back to you in just a second. A 2x4 is 100 centimeters wide. I just measured it. Here it is, more careful. What is the closest tick mark? 100 centimeters. I'm using the 1 meter side of the ruler. And the closest tick mark is 100 centimeters. According to my measurement, that 2x4 is 100 centimeters wide. And it is 100 centimeters wide. Now you're thinking, yeah, Sally, it's not 100 centimeters wide. You've never seen a 2x4 before. I just measured it. It's 100 centimeters wide. Well, Sally, that's a pretty bad measurement. How do you know? How do you now? If I report it honestly, I would have to say that it was 100 centimeters plus or minus 100 centimeters. 100 centimeters plus or minus 100 centimeters. And then you would know that it was bad, wouldn't you? You would look at it and you would know. You hardly know at all. Why are you saying something like that? I'd be like, oh, sorry. I just have this terrible ruler. It only has one tick mark on it. What can I do? And then, of course, the answer is that we must do better. And so we devise a better way to measure. We have a community of scientists who discuss the width of 2x4s, and they agree that that's not so good and we should try harder. So here I've made a measurement. I didn't line that up very well. Here I've made a measurement of this 2x4, and I report it honestly. And I say that it is 8.8 plus or minus 0.1. And the bad measurement, I guess we could say, is 100 plus or minus 100. That's pretty bad. It's in centimeters. For our purposes of talking about measurements and their associated uncertainties, this part of the number, the 8.8 part, is the measurement. The 0.1 part is the uncertainty. You can also say error. For our purposes, the word uncertainty and the word error are equivalent to each other. You may have a different idea in your mind of what error is, particularly during laboratory experiments in chemistry. But for our purposes, that 0.1 is the uncertainty, it's the error. I'll probably flip-flop back and forth. So I have an uncertainty of 0.1, and that's not surprising because my measuring device has a precision to 1/10 of a centimeter, and so my uncertainty is 1/10 of a centimeter. The uncertainty and the precision of the measuring instrument used to make the measurement are inherently linked. And so, when I make my measurement, I make it to tenths because the ruler goes to tenths, which means this measurement and its uncertainty should always have precision that matches. Always. Always, 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 always. This is the first little aspect of the skill that I expect you to have, is recognizing that numbers written with associated uncertainties should always have their precision match. The precision must always match because the uncertainty is indicative of the precision of the measuring, and the measuring instrument was to make the measurement. Precisions must match. This uncertainty is called the absolute uncertainty because the uncertainty itself is measured as a certain number of centimeters. There's another way of representing the uncertainty in a measurement. Instead of representing it as plus or minus 0.1, the absolute uncertainty, I can write it as a relative uncertainty, sometimes called the percent uncertainty, which is the ratio of the uncertainty to the measured value multiplied by 100. Here's how you calculate that. It's quite simple. I'll take the uncertainty, which is 0.1, and I've got my calculator here, 0.1, and I divide by 8.8, and I get 0.0136. Here on the slide, I've written that that's approximately 1%, which it is. It's 1.134%. So I'm going to write this as 8.8 plus or minus 1.14%. That's a legitimate way of writing that number. They're both legitimate ways of writing a number scientifically. Why have two? Well, it's really important in science because imagine that we do an experiment where we make measurements of position over here. And there's a certain uncertainty. There's a particular uncertainty of that measurement. And over here in the same experiment, I make a measurement of time. That time has an uncertainty of measurement because all measurements are uncertain, but they have different units. So how do I compare those two measurements? Well, if I calculate the percent uncertainty in position and percent uncertainty in time, whichever one has the higher percent uncertainty, whichever one has the higher relative uncertainty is the poorer measurement. A measurement that has a low relative uncertainty is a good measurement. A measurement that has a high relative uncertainty is a bad measurement. Sometimes it's bad, not because someone was careless. It's because the measuring instrument lacks precision, or it's because the thing is hard to measure. Imagine I asked you to take your pan balance in chemistry and measure the mass of an electron. That's a tricky thing to do. And so I would imagine that the uncertainty would be large. So a large relative uncertainty doesn't mean bad people. It means bad measurement. It means bad measurement. So now I know that I have to write these numbers, scientific measurements with the associated uncertainty, and it's simple to do, isn't it? It's simple to do. You measured the length and the width of the table to the centimeter. Some people may have measured it to the millimeter. But if you measure the length and the width of the table to the centimeter, then your measurement is plus or minus a centimeter. That's simple, right? And honest about yourself. Here's the next aspect of it. Once I make some measurement, every once in a while in science, you make a measurement and say, hey, look, I measured a thing, and that's it. But more often, I measure a little of this and a little of this and a little of this, and I bring them together and I calculate something using the measurement. For example, I have a rectangle, like this big green rectangle here, or like your desk, and I measure its length and its width, and I want to calculate the area from those. Well, I know that the length is uncertain, and I know that the width is uncertain. My question, how uncertain is the area? Because I'm going to report the area, and I have to say how uncertain it is. So, here's a skill. Consider that I make these measurements, and these measurements are a little bit silly. The width of the rectangle is measured to be 53 plus or minus 2. Now, you didn't see me make that measurement, but just looking at it, you can figure something out. The measuring instrument that I used to measure it had tick marks every 2 centimeters. That's weird. Who sells a ruler has tick marks every... I don't think you could buy that anywhere on the internet. I don't think Amazon has a ruler that only has tick marks at 2 centimeters. But apparently I found one and measured the width of this rectangle to be 53 plus or minus 2 centimeters. And then, mysteriously, I took that ruler and threw it away and used a different ruler to measure the length, 126 plus or minus 1, because that ruler had tick marks. That ruler had tick marks every centimeter. I don't know why I would do that. Well, here I'm doing it for educational purposes. You wouldn't really do it in real life. So I have a measurement of the length and the width of the thing. Length and width. I want to calculate the area and know the uncertainty in my area. Well, here's how I'll go about that. I'll realize that because the width is uncertain, there's a certain maximum value that the width could be and a minimum value that the width could be. That is, if it's 53 plus or minus 2, it could be as big as 55 or as small as 51. There's a maximum and a minimum possible value for the width. Same for the length. If it's 126 plus or minus 1, it could be 127 or it could be 125. Because I know the maximum and minimum values of the length and the width, I can calculate using the equation that the area is the length times the width. I can calculate the maximum possible area. I'll do that by taking the maximum possible length, 127, and multiplying by the maximum possible width, 55, and I get 6,985 square centimeters. That's the biggest it could possibly be, based on the uncertainty in my measurement. Similarly, I'll calculate the minimum area by taking the minimum possible length, 125, and multiplying by the minimum width, 51, and getting 6,375. A smaller area. Not surprising because I used the smaller measurement. So now I know the biggest possible area and the smallest possible area. And I know that there's a range between those two numbers, simply by subtracting, of 610 square centimeters. That is, the maximum area is 610 square centimeters bigger than the minimum area. But the actual area is in the middle, right? So I'll take that range, that is the 610, and divide it by 2, 305, and add that or subtract it from the actual area. Well, where does the actual area come from? Well, to get the actual area, I just take 53, which is my original measurement, and multiply by 126, much in the same way that you did when you did the area of the table. When I do that, I get 6,680, and now plus or minus 305. You know I'm not done, because this was previously pointed out. 6,680 is the wrong number of significant figures. It's the wrong number of significant figures because 126 has 3 significant figures. 53 has 2 significant figures. So my answer can only have 2. So I'm going to have to round my answer to 6,700. But it goes further than that. I have to round my answer to 6,700, but also I pointed out that the precision of the uncertainty must always match the precision of the measurement. So when I round 6,680 to 6,700, so it only has 2 significant digits, I have to round the uncertainty, not for significant digits, but so that the precision matches. Because 6,700 is precise to the hundreds place, because 6,700 is precise to the hundreds, I have to round 305 to 300. Oh no, Sally, all those wonderful digits you lost. You lost all those numbers. Those numbers weren't significant. Those numbers didn't. So, when I report the area of the table scientific, that is my answer. If you come back to me and say that the uncertainty in that measurement is unacceptable, perhaps the uncertainty in that measurement makes it so that you can't draw a conclusion about the nature of the areas of tabletops. I don't know why you'd be studying that, but well, then we have to devise a better experiment where we make more precise measurements that are less uncertain so that we can draw a more valuable conclusion. That calculation is honest. Okay, Shelley, I get it. The skill that I need to have is I need to be able to calculate the maximum possible, the minimum possible, subtract those two numbers to get the range, divide by 2, make that the plus or minus, fix the significant digits, and match the precision. That's the skill. It could be, but it's not. It's not, because something really, really interesting and funny is happening in these numbers. Just out of curiosity, I have a look at the relative uncertainty in my measurement of the width. And where I get that is I take 2 and divide by 53, multiply by 100. It's 3.77. 3.77% uncertainty in the width. Relative uncertainty, right? The absolute uncertainty was perfectly fine. That was good. The relative uncertainty is 3.77. I can also get the relative uncertainty of the length. I just have to take 1 and divide by 126, multiply by 100, and that relative uncertainty is less. And that doesn't surprise me for 2 reasons. One, when I measured the length, I used a more precise measuring instrument, and so that I have less uncertainty does not surprise me. You use a better instrument, you get a better measurement. That doesn't surprise me. Also doesn't surprise me because when you measure a larger thing, the relative uncertainty is going to be smaller. Large things are easy to measure. Small things are difficult. So it doesn't surprise me that they're different. Down here, 6,680 plus or minus 305. That was my result before I rounded for figures and precision. The relative uncertainty of that can be computed by 305 divided by 6,680 times 100 is 4.57. Does anybody see? Came together how? There's a name for it, the math folks say. Add. I discovered that hiding underneath all of this maximum and minimum and range and do and whatever and doing all that, underneath all of that, there was a generalizing principle at work. And it is whenever you multiply or divide numbers with uncertainty, the relative uncertainty of the result, the sum of the relative uncertainty. Whenever you multiply or divide numbers that have uncertainty, the relative uncertainty of the result is the sum of the relative uncertainties. That is how I do uncertainty calculations. Now, this has been a little bit dry and a little bit mathy. So if you find yourself feeling drowsy, now is the time to wake up. Because what I'm going to do now is I'm going to demonstrate the skill that I expect you to have. Next Wednesday, we'll have a quiz. And on that quiz, you will demonstrate your skill at what I'm about to demonstrate here for you. Now, along the way, you'll say, well, Shadi, I want to have more practice. Well, yeah, we'll make sure that you get lots and lots of practice. And we do lots and lots of problems as examples. But this is the very first example of me demonstrating this skill in its final form. So careful thinking and attention. I need a problem to solve. And so here I have an example that is somewhat familiar. A bedroom is measured to be 3.55 plus or minus 0.05 meters by 4.70 plus or minus 0.05 meters. How many square meters of carpet would be needed? So I'm calculating the area. So I have a rectangular region that is this bedroom, and I'm going to calculate the area. And the problem that I'm trying to solve is what is the area and its associated uncertainty. To do that calculation is going to require many steps. And I think that students in your position have struggled with this in the past because of the very large number of steps that are required in order to accomplish this calculation. So as I demonstrate this calculation over here, I'm going to write a list of steps to help us along to make sure that we do everything in order the way that it needs to be done to get the correct result. This list of steps will be valuable to you when you're solving problems on your own or when you're following along watching me do uncertainty problems, because it's the same steps every single time I use measurements and their associated uncertainties in a calculator. So the first thing I'm going to do is collect my information here. I have a bedroom and I've got these two measurements. I'm assuming that the longer measurement we would call the length and the smaller measurement we would call the width. So here I'll say that the width is equal to 3.55 plus or minus 0.05 meters. This measurement tells me something about the measurement itself. It tells me about the measuring device that was used and that it had tick marks every 500th of a meter. I don't know where you get one of those, but it had tick marks every 500th of a meter. That precision of the instrument determined the uncertainty in the measurement that I write there. The length, it happens, in this example, the room is nearly square, but a little bit longer. is 4.70 plus or minus 0.05. I think they used the same instrument to measure both dimensions. That would make sense. You measure the width and you measure the length. You do it all in one go. And what I'd like to do is calculate the area. Now, we already know, everybody knew before they showed up today, that the area is the length multiplied by the width. Everyone knows that equation for the area of a rectangular region. Now, the question, what is the area of the room and its associated uncertainty? That is the question. Step one, you're gonna like step one. Step one is the easiest of the steps. Step one, just do it. Just calculate the area, pretending like significant figures and uncertainty never happened. We never had this discussion. Nothing matters at all. If you'd like, calculate along. I'd appreciate it if you'd catch me in errors, but also make sure that you know how to do the calculation yourself and that everything. So I'm going to take the length, which is 4.70, and I'm going to multiply it by the width, which is 3.55, and I'm going to get the area, 16.685. 16.685. Yay, I did it. I know the area. Well, now you realize, because you're educated now, that that is no good at all. That's not how we do that. We have more work to do. The next thing that I'm going to do, and I'm going to abbreviate, if you don't mind, the things on my list, number 2 on my list, is to calculate the relative uncertainty of each of these measurements. I have the absolute uncertainty. I would like to know the relative uncertainty of the measurement. So in the first case, the width here, what I'm going to do is I'll take the uncertainty, the absolute uncertainty of 0.05, and divide it by 3.55, and then multiply that by 100. I just did that in my calculator. Of course, I could do that in my head. I should use my head to do math, my calculator to do arithmetic, but it's 1.41%. You see that? It's 1.408, but I'll round that to 1.41. 1.41%. So I'm going to put a little arrow here, call this 1.14%. That is the relative uncertainty of this measurement. I've been doing that today. Thank you for catching me. I've been doing a little numeric dyslexia, which is actually called dyscalculia. Getting your numbers all mixed up. I think it's called dyscalculia. If not, I just made up another word, which I have a tendency. And calculate the relative uncertainty in the length. The relative uncertainty in the length is 0.05 divided by 4.7 times 100, which is 1.06. Those relative uncertainties are similar. That doesn't surprise me. They're similar because I measured a similar thing with a similar instrument. As a matter of fact, I measured a similar thing with the same instrument. So I got similar relative uncertainties. Is no surprise at all to me. No surprise at all. Next step, step number 3, is to apply the rule of uncertainty. Now, you're going to hear me say the rule of uncertainty many more times before your quiz. Here I go, deep breath. When you multiply or divide number with uncertainty, the relative uncertainty of the result is the sum of the relative uncertainty. Which means, since I'm multiplying the length and the width together, I should add their relative uncertainty, 2.47%. And so that is the relative uncertainty of the results. I'll simply transfer it down here, 2.47%. Knowing the relative uncertainty of the measurements made it possible for me to determine the relative uncertainty of the result. Excellent. But I'm not finished. Relative uncertainty is nice, but I would like to know the absolute uncertainty. The relative uncertainty is nice, but I'd like to know the absolute uncertainty. And so what I'm asking is, what is 2.47% of 16.685? Now, hopefully you've been well trained in math and know how to take a percentage, but in case it's a mystery, I'm going to take 2.47 and I'm going to divide it by 100. And I get 0.0247, of course. And then I multiply that by my measurement, 16.685. And my calculator tells me that my area is actually 16.685 plus or minus 0.4121 and a bunch more digits. Woo! Thank goodness we're done. We're not done. We're not done. All along, I've been ignoring the fact that significant figures matter. But when it comes to significant figures, I wait until the end. Step number 5. Step number 5 is to fix the sig figs. And to know how many significant figures my answer should have, I look to my measurements. 3.55 has 3. 4.70 has 3. But Charlie, it's ambiguous. That 0 there, is that significant or whatever? Well, if you've written down your rules of uncertainty, they would tell you that yes, it is, but I have an even better reason. If I take 4.70 and I add 0.05 to it, that 0 is not going to be a 0 anymore. It's significant. If I subtract 0.05, that 0 is not going to be a 0 anymore. It's significant. It matters. They both have 3. And so my answer can only have 3. I've got 5. So I need to round my answer to only 3 significant digits. That's 16.7. No, Charlie, you're losing digits. Is wonderful digits. They didn't do anything. Well, they're not significant. They don't matter. They don't carry any information, no reality, and so they got to go. Oh, I get it. Now I'll round this one to 3. This is the number one mistake that honors in this calculation. The number one mistake. This is a moment. Don't be that guy who makes this. When it comes to the uncertainty, the issue is not significant figure. I'm not going to round this to 3 significant figures. No. The issue at the end, step 6, is precision. Precision is the answer. I need to match the precision of the uncertainty to the precision of the measurement. My uncertainty is precise to the 10th place. Matching the uncertainty. The measurement is uncertain to the 10th. And so the uncertainty must be rounded to the 10th place, so that the uncertainty precision and the measurement precision match. And then this would be, what were the units of these? And so this is going to be meters squared in the end, and that is the area calculated scientifically. Naturally, becoming skilled at this is going to require some practice, and you would guess that as your teacher, I'm going to give you an opportunity to practice.